This is a video lecture for Math 181 for Monday, April 20th, and the topic today is indefinite integrals. So we've been talking about definite integrals. Well, what is an indefinite integral? And the definition of an indefinite integral is if you have an integral sign, but it doesn't have limits on it, that's key, of f of x dx. Okay, and this equals some function capital F of x. This means that f prime, the capital F prime of x equals f of x, or in other words, f of x, capital F of x, is the antiderivative of f of x. This is the definition of an indefinite integral. The big difference here is we don't have integration limits. And so what is the difference? Let's talk a little more about this difference. If I have some definite integral, a definite integral would have integration limits of f of x dx versus an indefinite integral which has no integration limits. Okay, what is the difference between these two things? Well, this is a definite integral, and this is just a number. And this is a function. Okay? So again, a definite integral has integration limits, and you're trying to calculate a numerical area under this curve from a to b. This is just a number. Whereas you can also have an indefinite integral, which doesn't have integration limits. And the indefinite integral of f of x dx is really a function, and that function is known as capital F of x, which is the antiderivative of lowercase f of x. One point I want to make about this is, let's talk about antiderivatives some more. Earlier we found that f of x, capital F of x, equals x cubed over 3 is the antiderivative of lowercase f of x equals x squared. I believe this was an example problem we did. We found that this is the antiderivative of this. And what that means is, if we take f prime of x, we take the derivative of this, we get 3 times x squared over 3, which equals x squared, which equals f of x. So this is in fact the antiderivative, f of x of x cubed over 3 is the antiderivative of lowercase f of x equals x squared. Here's a point though, what if capital F of x was equal to x cubed over 3 plus some constant c, okay? What if instead of f of x being x cubed over 3, it was x cubed over 3 plus some constant c? Let's take the derivative of capital F of x. So the derivative of capital F of x is now 3 times x squared over 3. Okay, and then the derivative of a constant is 0 plus 0, which equals x squared. So this is also the antiderivative of f of x. What happened here? Basically, for antiderivatives, you can always tack on a constant to the function, the antiderivative function, and it will still always be an antiderivative of your original function under the integral sign. So while this is a valid antiderivative of x squared, x cubed over 3 plus any constant, 2, 3, 11, a million, is still a valid antiderivative of x squared. And this c is called an integration constant. And so the most general, what this means is, that the conclusion of this is the most general antiderivative capital F of x always includes an integration constant. This always includes an integration constant. The most general antiderivative, f of x, always includes an integration constant. And as we'll see, what that means is when we evaluate an indefinite integral, when you evaluate a definite integral, you don't need an integration constant because the answer is just a number. But when you evaluate an indefinite integral, which evaluates to not a number, but an actual function, we always have to include an integration constant to make it the most general antiderivative. Let's do some examples of this. I think this will make sense to you guys once we do a couple of examples of indefinite integrals. Okay, so I have a couple examples for you guys. One of them is this. Let's find the indefinite integral of x to the fourth minus 3x squared. Again, because there's no integration limits, this is not a number. It's not an exact area under a curve. It's a function. It's a function, okay? And let's use the rules we've learned here. So we're trying to find an antiderivative function to this. What is the antiderivative of this function? Well, let's use that rule where, if you guys remember, there's a rule where we have x to the n, the antiderivative is x to the n plus 1 over n plus 1. So we're going to use that rule here. Here we have x to the fourth. So in this case, n is 4. We do x to the 4 plus 1 divided by 4 plus 1. I'm going to erase this. It is just a reminder of our shortcut rule here. X to the 4 plus 1 over 4 plus 1 minus 3 times, now here n is 2, so we do x to the 2 plus 1 over 2 plus 1, okay? And then finally, we need to add an integration constant because, as we said, the most general form of an antiderivative of this function always includes an integration constant. And then we can simplify this, and this comes out to x to the fifth over 5 minus these 3's cancel, minus x cubed plus c, and that's our answer. This is now the function, the antiderivative function to this indefinite integral. Let's do another example. What if we have this function here? As an indefinite integral, what is the antiderivative function to this indefinite integral? Well, this looks a little bit tricky. I'm not really sure how to guess what the antiderivative to this function is. But what I can do is I can rewrite this as 1 over cosine of theta times sine of theta over cosine theta d theta. I can rewrite this and then identify these two things separately. The first thing here is secant of theta. The second thing is tangent of theta, d theta. Okay, and now can you guys guess a function, the antiderivative of secant of theta, tan theta? In other words, can you guess a function such that when you take the derivative of it, you get secant theta, tan theta? Well, the answer to that is, if you guys remember, the derivative of secant theta is secant tan theta. And so the antiderivative of secant theta, tan theta is just secant theta. So the answer to this is secant theta plus c, okay? And that's our answer. Now, if you're not unsure whether you have the correct antiderivative here, we can always take a derivative of this. Let's take a derivative of this antiderivative. Okay, and if we do that, the derivative of secant theta is secant theta tan theta. The derivative of c is 0, so we get this, which is what was originally under the integral sign, and so this is our correct antiderivative. Let's do one more example. I want to do this one. okay, this is actually a definite integral, so you might wonder, well, what am I doing here? But what we can do is use the new technique. We can kind of do this in two parts. What we can do is first we can treat this as an indefinite integral and find the function, the antiderivative function to this indefinite integral, and then at the end we can plug in our limits. Okay, so this is important to see how to do this. So what I can do is try to find the antiderivative function to this function. Now what I'm going to do here is simplify things. And the first thing I can do is, this looks kind of scary, but I can divide every term here by x, because x is in the denominator. And so if I do that, I get x plus x to the 1/2. So x plus, these two x's, this x cancels here, we get an x. These two x's cancel, we get an x to the 1/2 here, or square root of x. And then over here, what happens is we get an x to the minus 1/2. Because square root of x divided by x is 1 over square root of x, which is x to the minus 1/2. We still have a minus 2 here. So I just simplified this way. And then I can try to find the antiderivative to this function, which, if you guys look at our rule here, let's use our rule where we always use that rule, what is it, x to the n. The antiderivative is x to the n plus 1 over n plus 1. So for our x here, we get x squared over 2. For x to the 1/2, we're going to add 1 to 1/2, so we get x to the 3/2, right? 1 plus 1/2 is 3/2, over 1 plus 1/2 downstairs over 3/2, minus 2, and now we have x to the minus 1/2. We're going to add 1/2 to minus 1/2, which gives us x to the 1/2. And then downstairs we have minus 1/2 plus 1. So that gives us 1/2, okay? And then instead of adding integration constant, since this is actually a definite integral, what we do is we draw a vertical line here, and then we include our integration limits, okay? Now I'm going to simplify this a bit, just kind of clean this up. This is x squared over 2, plus if I move this, if I multiply the reciprocal, I get 2/3 x to the 3/2. Minus, multiply the reciprocal here, I get 4x to the 1/2. And then this vertical bar, which means evaluated at the endpoints of 1 and 3. So now I'm going to plug in my endpoints, and I get 3 squared over 2 plus 2/3 times 3 to the 3/2 minus 4 times 3 to the 1/2. All of this now minus, now I plug in 1, I get 1/2 plus 2/3, because x squared, 1 squared is 1, 1 to the 3/2 is 1, so I get a plus 2/3, 1 to the 1/2, or square root of 1 is 1, so I get minus 4 here. And then I can simplify this, and if you guys do that, this comes out to 3.86. So this is the exact area under this curve from 1 to 3. Now again, this was a definite integral, but I used this new idea of, I treated this as an indefinite integral to first find the function that was the antiderivative of this function, and then I put this vertical bar and I plug in my limits. And this is usually how most people evaluate definite integrals, is they find the function, the antiderivative function, and then they plug in the limits of 1 and 3. And so we get a number here. If I was interested in just the indefinite integral, I'd take away these numbers, and this function would be my antiderivative, plus I'd have to tack on an integration constant. Okay, hopefully this made some sense to you guys. This is part 1 of our video. Part 2, we're going to deal with something called the net change theorem. All right.